Welcome back to linear algebra. In this video, I want to talk about invertible transformations. That is, linear transformations which have an inverse. I've got a wall of text behind me already reminding us of some of the basic ideas. Let me get myself out of the way so we can talk through it. If we have a linear transformation t, we've established previously that every linear transformation is a function. One of the key ideas of a function is that if we have two equal vectors, v1 equals v2, and we take the transformation, we get the same thing out. T of v1 is equal to t of v2. And we've established in previous mathematics courses, calculus, college algebra, maybe somewhere earlier than that a function is invertible. It has an inverse if and only if it is a one-to-one function, which takes this definition and kind of flips it around. If t of v1 is equal to t of v2, then v1 is equal to v2. You are likely more familiar with this definition, thinking about graphs of real numbers. The cubing function is one-to-one. Given any particular output value, y value, there is exactly one input value that makes it work. Compare that with the squaring function, which is not one-to-one. For a particular output, a particular y value, there are two different inputs that work. So the cubing function is one-to-one, the squaring function is not one-to-one. The cubing function has an inverse, the squaring function does not have an inverse. And we know the definition of an inverse function. The inverse of t is another function written as t raised to the -1 power, right, as t inverse, and it's going to map in the other direction, from w to v. And we want that t of t inverse of vector w is equal to w, and t inverse of t of vector v is equal to vector v. Right? That's what it takes to have an inverse. And finding inverses of functions is something that we can do. It works. But what I really care about in this video is when is there an inverse function, right? Finding an inverse function is not the interesting idea here. And so let's dive right in. A theorem here says that a linear transformation T is one-to-one if and only if the kernel of the transformation is equal to 0. This is an if and only if statement, so the proof is going to go both ways. But before I get to that proof, again, not stated in this theorem, but the important thing, a linear transformation is a function. A function has an inverse if and only if it is one-to-one. So when we say that the transformation is one-to-one, we really are saying that the function has an inverse. Sometimes I hate mathematics because we don't state the things that we care about. We care that the transformation is invertible. It is invertible if and only if it has an inverse. I claim that it is one-to-one here. It has an inverse if and only if the kernel is the 0 set. So to prove this, it's going to take two parts. First, let's assume that t is 1-to-1. This is the easy half of the proof. Since t is a linear transformation and linear transformations preserve linear combinations, it has to be the case that t of the 0 vector is equal to the zero vector. And things immediately get messy, and they're just going to get messier here. When we're talking about the zero vector, we have to be careful. I don't know a lot about V and W. I don't know if they are the same vector space. I don't know if they have the same definition of the zero vector. And so whenever I write the zero vector, I have to make sure I know which one I'm talking about. This is the vector being acted on by transformation T. So this is a vector in V. This is the result of the transformation. So this zero vector is a vector in W. Now, kernel is the set of vectors in V. So this zero is this zero. This is a vector 0 in V. Right. We have used so far the fact that T is a linear transformation. If T is a linear transformation, that first line has to be true. And it's important to establish that first because I want to pick a vector out of the kernel. I know that the zero vector is in the kernel. I don't know if there is anything else. Well, I'm hoping to prove that there isn't anything else, but I don't know that yet. So I know that the kernel contains vectors in V. To make it clear that that's where this is coming from, I'm going to call this vector out of the kernel little v. It would be nice if I could show that it has to be the zero vector, but I don't know that yet. I do know the definition of the kernel, though. The kernel is the set of vectors that map to the zero vector. So because v is in the kernel, t of v must be the zero vector, right? And again, this is the zero vector in W, which is useful because I have over here something else that is equal to the zero vector in W. So by substitution, t of v has to be equal to t of 0. Finally, the assumption that I started this proof with was that t is a one-to-one function. And since t is a one-to-one function, then the only way for this to work is if the arguments themselves are equal, which means that v is equal to the zero vector. And so with that, we have shown that anytime you take a vector out of the kernel, you have to have taken out the zero vector. The only way that works is if the only vector in the kernel is in fact the zero vector. Right. That's my first direction. Now I have to show the other direction. Let's assume instead that the kernel of t is the zero vector, and this time prove that t has to be one-to-one. Well, what does it mean to be one-to-one? A function is one-to-one if we have a situation like this. Now we know we can pick vectors v1 and v2 so that t of v1 is equal to t of v2. It's always possible that we picked the same vector for both v1 and v2. But we don't know that yet. We just know that we have some. To show that the function is one-to-one, we want to show that v1 is equal to v2, but we don't know that just yet. In order to get there, I'm going to do some creative rearranging. The only thing that I know right now, I know I have a linear transformation, so I'm going to try to use properties of linearity at some point. And I know that the kernel is the zero vector. So if I can get transformation equals 0, that's going to put me in a very good place. It's actually pretty easy to do that. If I rearrange this equation, I can write it as t of v1 minus t of v2 is equal to the 0 vector. And again, that is the 0 vector in W. And then I can use the linearity to say that t of v1 minus t of v2 is t of v1 minus v2. Because it's a linear transformation, that means we can do this. That's what linear transformation means. And so I have linear transformation acting on thing gives me the 0 vector. By definition, that must mean that v1 minus v2 is in the kernel of t. Right? That's what it means to be in the kernel. Transformation acting on it gives you the 0 vector. But since the kernel of t only has the 0 vector in it, that means that v1 minus v2 itself has to be the 0 vector. And again, paying attention, this is the 0 vector in v, not the 0 vector in w that we were using before. Which is important because we're subtracting some vectors in v, the result should be in v. All right, it always works, it should always work, but paying attention and making sure you know which 0 is which will help you understand what's happening here. Not paying attention to that and forgetting the fact that I have 0 meaning two slightly different things is an easy way to confuse yourself trying to read this proof. But I can rearrange that equation pretty quickly to get that v1 is equal to v2. And that gives us exactly what we wanted. I picked arbitrary vectors in v so that t of v1 was equal to t of v2. And I showed that the only way that could work is if v1 and v2 themselves are equal. That's the definition of one-to-one. I've shown that this works in both directions. That concludes the proof. I know that when the kernel of t is equal to the 0 vector, when there's only one element in the kernel, I have a one-to-one function. And when I have a one-to-one function, again, I have an inverse. So transformation is invertible, kernel is 0, are equivalent statements. The next theorem here is a little bit messy. Let's consider a linear transformation T mapping from V to W, where the dimension of the domain and the codomain are equal. Then I claim that T is one-to-one if and only if T is onto. The definition of an onto function or an onto transformation is that the range is the codomain. Every vector in the codomain happens to fall into the range. And so again, we have an interesting theorem that is not telling us what we actually want to know. The point of this theorem is this onto condition is a new way of finding one-to-one, and the only reason we care about one-to-one is because that makes it invertible. If you have an onto transformation, if you have the dimension of the domain and codomain are equal, and everything in the codomain falls into the range, then you have an invertible transformation. That's what this theorem is trying to tell us. I want to mention one last piece of vocabulary here, which is not really important to this lesson, but I think it's something that's worth seeing at some point, and this is a natural place to bring it up. A bijection is a function which is both one-to-one and onto. In general, outside of the realm of linear algebra, it is a bijection that you're going to care about when you're looking for something that has an inverse. Linear algebra has this really nice trick that I just put the theorem on the board that lets us have one as soon as we have the other, makes our lives a lot easier. In general, that doesn't happen. And so this idea of bijection, finding both of these things, is going to be important for anyone who's moving onward in mathematics, or for anyone who is taking discrete mathematics alongside of this course. Bijections are a lot more important there when you're looking at a much broader class of functions than just linear transformations. But for right now, this idea is what we're looking at. And in order to prove this, we're going to have to take a relatively long route. Before I can get to the theorem, I actually have to prove a separate lemma. Actually, before I even state the lemma, let's state a little bit more in the way of vocabulary. We've talked about the rank and nullity as classifications of matrices. Here, I'm going to use them as classifications of transformations in general. And the definitions are going to be a little bit different, but in the same direction. The rank of a transformation is the dimension of the range of the transformation. And the nullity of a transformation is going to be the dimension of the kernel of the transformation. That second one I think is a little bit more obvious. The kernel fills nicely the space of the null space. We talk about a null space for a system of equations. We talk about a kernel for a transformation. But in either case, it's the places where you take an operation, put it on a vector, and get out 0. The rank we talked about before as being the row space of a matrix, the dimension of the row space. And I kind of hinted at, without really proving, that the rank, or that the row space, was the range of the transformation. And so there is some basis there, although a little bit less. And the lemma that comes as a result is something we have seen before. The rank of T plus the nullity of T is equal to the dimension of V. I'm not going to prove this entire theorem, but I'm going to get you far enough that I think the rest of it should make sense to you. Let's let M equal the dimension of V. So we just give a name to that. And it's now a page off screen, but in our original theorem, remember that the assumption we made is that the dimension of V and the dimension of W are equal. So N has to also equal the dimension of W. And then let's let K equal the dimension of the kernel or the nullity. Right? The nullity is the dimension of the kernel. And since the kernel of T is a subspace of V, the dimension of the kernel has to be smaller than the dimension of the vector space. So K is less than or equal to N. My proof is basically going to assume strictly less than, just because the or equals case is really messy to try to write out as a special case. Technically, my proof will still work in that case. It just would look really strange. Um, but that's something I'm going to just accept for the sake of getting enough of this proof out without bogging us down in the details. All right, so far I'm just giving label to some things that I think are going to be useful in a little bit. We have names of dimensions of some things. The dimension of a vector space is the number of vectors in the basis. Since we know that the dimension of the kernel of T is K, then there has to be a set of linearly independent vectors, K of them, V1 through Vk, which form a basis, right? That's the definition of a basis. If you have a set of linearly independent vectors that span the set, there are K of them. And since the kernel is a subspace of V, these are linearly independent vectors in V, which is why I named them V1 through Vk. And if I take the same V1 through Vk, and I introduce a few more, Vk plus 1, all the way down through to Vn. Right? V1 through Vk are already linearly independent. If k is smaller than n, then there are not enough vectors to span the entire vector space. But if we start putting in more linearly independent vectors, eventually we'll get a set of n linearly independent vectors, and they will span the entire vector space. So this forms a basis for the entire vector space. Right? We know that any basis for the kernel has k vectors in it. We know that any basis for the vector space has n vectors in it. And because the kernel is a subspace, we know that there is a basis for the entire vector space that contains the basis for the kernel. Anytime you have a subspace, there's always a way to do that. And the reason that I care about doing this, if I pick some random vector in my vector space, I can write it as a linear combination. C1 V1 plus C2 V2 plus, I need to fill in the middle steps here. We're going to have CK VK. We're going to have CK plus 1 VK plus 1. Let's try writing that again in a way that actually is legible. There we go. And eventually we get all the way down to Cn Vn. That's really quite a mouthful. But the reason that I want an arbitrary vector in V is because I'm looking to analyze the range of the transformation, right? Those are the three things we talked about: the domain, the codomain, the kernel, and the range. So if I take T of U, well, that's just T of this linear combination. And since T is a linear transformation, it preserves linear combinations, and I can spread this out. C1 times T of V1, C2 times T of V2, CK times T of VK. I'm hopefully not going to run out of room here. CK plus 1, T of VK plus 1, Cn T of Vn. All right, I fit that all on the screen. And finally, the reason that I set up my basis the way that I did, I know that there are k of these basis vectors which are in the kernel. And remember, the kernel is the set of vectors that transform to the zero vector. So those first several terms go away. I start with CK plus 1, T of VK plus 1, and I continue downward to Cn T of Vn. There were n vectors. K of them turned out to be the zero vector. This is a linear combination of n minus k vectors. I'm not going to prove that these vectors are linearly independent. I'm going to ask you to take me at my word on that. And if I had more time, I would probably go through it. It's not that bad. It's just not interesting, and this video is long enough. We can show that these vectors are linearly independent, and if we did show that these vectors were linearly independent, then they would form a basis for the range T of V. So the rank of T, which is the dimension of T of V, is equal to n minus k. And that's the point of all of the algebra we did, which finally we can write. And the theorem told me I wanted to look at the rank of T plus the nullity of T, which is n minus k plus k, which is n, which is the dimension of V. All right, that proves my lemma. The rank of T plus the nullity of T is the dimension of the domain. But remember my theorem. Let's scroll way up here. I'm just going to copy it and reuse it. My theorem up here says that if I have a linear transformation where the dimension of the domain and codomain are equal, then my transformation is one-to-one if and only if it is onto. So let's go ahead and copy that theorem down here where we can start building off of it now that we have our lemma as our starting point. Right. So let's first assume that T is one-to-one. This is an if and only if theorem. We could prove this using two directions. Assume T is one-to-one, prove that it's onto. Assume T is onto, prove that it's one-to-one. But this is actually one that I can prove by a sequence of if and only if statements. T is one-to-one if and only if the kernel of T is the singleton 0. And the kernel of T is the singleton 0 if and only if the nullity of T is equal to 0. Right? We proved that first statement, one-to-one if and only if kernel is the singleton. The nullity is the dimension of the kernel, and the dimension of the singleton is 0. So, so far, fairly straightforward. But we also just proved T is onto if and only if, well, that would be that W is T of V. The codomain is the range. And in fact, this is true if and only if the dimension of W is equal to the dimension of the range, which is in fact the rank. That's not obvious as an if and only if statement, but it will make sense when you add in the reminder that T of V is always a subspace of W. So T of V must be contained within W. The dimension of T of V must always be less than or equal to the dimension of W. And the equality of the dimension happens whenever the vector spaces themselves are the same vector space. So T is onto if and only if the dimension of W is the rank of T. But from our statement of our theorem, the dimension of W and the dimension of V are the same. So I get that the dimension of V is equal to the rank of T. And that's it. Finally, we invoke our lemma. Since the rank of T plus the nullity of T is equal to the dimension of V, the last thing I can say is that the nullity of T is equal to 0 if and only if the rank of T is equal to the dimension of V. So we have a bunch of if and only if statements. The function is one-to-one if and only if the nullity is 0. The function is onto if and only if the dimension of V is equal to the rank. And the nullity is 0 if and only if the dimension of V is the rank. Therefore, T is one-to-one if and only if T is onto. Sorry, I didn't mean to bring myself up just yet. I wanted to close off this proof first. That's our proof, that's that result. Now I want to bring myself back on camera. We could continue onward. There's other things we could prove that will build up this nature, but for right now, that's good enough. We're interested in knowing when a transformation has an inverse. We know that a transformation has an inverse when it's one-to-one. We know that a transformation has an inverse if the kernel is 0. We know that a transformation has an inverse if it is onto, which is the same thing as saying we know that the transformation has an inverse if its range is the codomain. Using any one of those things is enough to show that a transformation has an inverse. This video is running a little bit long, so I unfortunately don't have enough time to show you an example of this myself, but I'd like you to try. Recall that an isomorphism what is a vector space? I don't know. But remember from our previous lesson, the canonical isomorphisms. If we have a vector space V, an n-dimensional vector space with a basis V1 through Vn, we can write an isomorphism, a change of basis from that to Rn by taking the kth basis vector and translating it to Ek, the column vector with a 1 in the kth position and a 0 everywhere else. I would like you to prove that this transformation is in fact invertible. Every isomorphism is invertible, and there is a way to set up every invertible transformation to call it an isomorphism, but that's a little bit beyond what I want. Show that the isomorphism transformation that we've established using basis vectors is always going to be invertible. There are a couple of options you can use here. I know this is a very general statement, so it's a little bit hard to see sometimes. There are some easier ways and there are some harder ways to deal with this. But use all the properties that we just showed and find one of them that will let you take this to invertible. Play around with that for a few minutes. I'll see you in the next video.